So to continue from last week, we're talking about the interior of the planet Earth. So as we spoke about before, the mantle is much less dense than the core. The mantle is rocky, but it has molten rock as well. If you remember from last week, it's like a melted plastic. The core, on the other hand, instead of being rocky, is actually metallic, consisting of a lot of iron and nickel. The outer core is a liquid metal, and the inner core is solid due to pressure. Remember, the outer core being a liquid metal is important, with the inner solid core rotating inside of it, which generates the Earth's magnetic field. And the lava that comes up from volcanoes is coming from the mantle, and this allows us to analyze the materials inside of the Earth. So, we also talked about this a little bit last week about the continental drift, a theory which Richard Wagner proposed, where basically we notice these things like the eastern part of South America fits nicely into the western coast of Africa. And we see the same features with the eastern coast of the United States with the western coast of Europe. And besides the superficial puzzle like appearance where the pieces seem to fit together, there's also strong evidence from the fossil record where similar creatures can be found in the fossil record on the eastern coast of, say, South America, compared to the western coast of Africa, and not really anywhere else. So that really is suggestive that these land masses were at one time joined together. So basically, we have two types of crust in the continental drift theory. We have heavy, dense oceanic crust, and then lighter crustal material, continental crust. And they kind of float along the mantle, but the convection underneath in the mantle is what's driving this process. And we get features like the Mid-Atlantic Ridge where the plates are actually drifting apart from each other compared to the western coast of North America, where we actually have a subduction zone, meaning this oceanic crust, because it's heavier and more dense than the continental crust, it goes underneath, and as a result we get volcanic ranges behind because of the melting oceanic crust coming underneath the continental crust and melting, and the heat and pressure needs to release. And we see this all along the Pacific plate, and this is often referred to as the Pacific Rim of Fire, where we get a lot of geologic activity, just like at the San Andreas Fault. Excuse me, where you get volcanoes and earthquakes. So, just like the Mid-Atlantic Ridge, where plates are moving away from each other from these convection cells, and then new oceanic crust forms at the rift and it spreads apart from each other, which pushes the two plates apart. So we can follow the tracks backwards from the motion they're having today. In fact, we can even measure how fast the North American continent is moving away from Europe in inches per year. So if you play the clock backwards, we see that the continents become closer and closer till we get to about roughly 200 million years ago, where we have the latest supercontinent called Pangaea. Now, the moon had a bit of a different history than the Earth. So, the moon has features that are called maria, and that was due to previous volcanic flows, which came and almost was like putting new asphalt down, and those areas look a little bit cleaner and blacker. And these lava flows could have formed from plate tectonics, but a lot of times they formed from huge asteroid impacts on the surface of the moon, which basically totally uh, melted the landmass and lava flowed to fill it in where the impact occurred. And we're left with these Maria, which look much more featureless than the other areas of the moon called regolith. And the far side of the moon, if we look at that, it looks relatively unmarked compared to the side of the moon which always faces us. Now, when we talked about the moon being responsible for the phases of the Earth, for the tides on Earth, and the moon actually used to be a lot closer to Earth, that actually caused this dynamical breaking and release of energy, is what caused the moon to have one face locked with always facing the Earth. That doesn't mean that the moon is not spinning, it's just spinning on its own axis at the same rate at which it goes around the Earth. So, crater formation on the moon is just like on Earth. So, basically, a meteoroid strikes the moon and it ejects material outward, and the explosion ejects more material, leaving the crater. So, just like on Earth, but unlike on Earth, the moon doesn't have weather patterns, which sort of erases the history of all of these impacts, and there's no active plate tectonics, the whole conveyor belt system that recycles oceanic and continental crusts. So we see, this history of the moon in the early solar system where collisions were much more frequent because material, it took time after the whole solar system was formed for the material to coalesce into the bodies, only leaving behind the asteroid belt. So craters are typically 10 times as wide as the meteoroid creating them and twice as deep. And that's because of the enormous amount of energy from the impact. And rock is pulverized to an even greater depth than the crater, which isn't a big surprise. Basically, all the material underneath what we can see also has a tremendous amount of energy dispersed through the surface and the lower layers where the impact occurs. Now, most of the lunar craters date back to about 3.9 million years ago, and we call this epoch the Late Heavy Bombardment, which was, as I said before, when a lot of the material of the Earth, of the solar system, was being coalesced by these larger bodies such as Venus and the Earth, and material. They basically swept it up like a vacuum cleaner and cleared out the orbits. So after this period, the frequency of collisions of asteroids became much less frequent. So on the surface of the moon, we can see both very large and very small lunar craters, which isn't a big surprise. And just like on Earth, you would expect many more small impacts than you would larger impacts, such as on Earth, there's almost a constant flux of dust grain material falling into Earth, and you might get an asteroid the size of a school bus once a year, something that's a kilometer across every million years. So, besides the Maria, the surface of the moon has this material called regolith, which is a thick layer of dust left by these meteorite impacts that basically vaporized the surface and threw it up as dust. And the moon, just like the Earth, is still being bombarded, and most frequently by very small micrometeoroids. So, to harken back to what we were talking about with this dynamo action of the Earth's interior metallic solid core rotating inside of the liquid outer metallic core, we have this magnetosphere that's generated. And that's very important because if we have the sun out here to the left, it has what's called the solar wind, which is this enormous flux of escaping charged particles like protons or helium nuclei that don't have bound electrons, and they're highly energetic. And the big thing that our Earth's magnetic field does is actually cause these materials to bend. Because remember, magnetic fields uh, can impact charged particles, so these charged particles are bent around the Earth's magnetic field, which is important. So if we look at these magnetic lines, we can see basically if you have a charged particle coming in, it will be bent along those lines. And it terminates at the poles, so this is where we see the aurora. If you're near the north or south pole, which you're seeing the charged particles being bent at the most extreme angles, and if we remember, charged particles that are accelerated emit light. So that's how we see these features of the aurora. So these charged particles are trapped in these bands, which we call the Van Allen belts, and they spiral around these magnetic field lines, never really reaching the surface or the atmosphere of Earth unless their energy is just too intense. So near the poles, the Van Allen belts intersect with the atmosphere, and this is where we see these charged particles escaping. And when they do, we see this glowing light called aurora. Now, how did the actual moon come to be? Well, older theories were that the moon was just a huge body that was mutually gravitationally attracted to Earth and sort of trapped there. Recent theories seem to, evidence has come up over the past 60, 70 years that really called that into question. Now the common accepted model is the giant impactor theory. So basically, the theory goes that the Earth was struck by a planet-sized object, roughly the size of Mars. And basically, when this happened, it came in and hit the Earth at a glancing angle, meaning it wasn't a head-on collision, and it caused a huge ejection of material from the Earth's mantle, and eventually over time this material that was ejected from this enormous collision coalesced under its own gravitational forces and became our moon. And if you look down in the links, I linked to a video which has a nice description and video about this. Due to copyright reasons, I can't really put that in a YouTube video. So, 4 billion years ago, the moon had many craters but no maria. But by 3 million years ago, the maria had formed, and they were also covered by craters. So basically, the maria formed from these lava flows, and then the material cooled, and then subsequent impacts from asteroids left behind their scars even in this melted lava flow regions. But this was at a time about 3 billion years ago when really the late heavy bombardment period had ended and a lot of the material had been already swept up by the planets. So the collisions are much less frequent. So that wraps it up for the history of the Earth and Moon system and a lot of basic geology I'm sure you're all familiar with. So thanks a lot, and go on to the next link, which I'll also give in the description, to Chapter 6. Thank you. Bye.